Okay, let's begin. That bell means we are on live. Okay, it's Saturday night. Does anybody know what I just said?
Saturday Night Live.
Oh my God, and that's from an Arab from the UAE. He knows what I mean. Excellent, wow. I'm very impressed. I wouldn't have thought that was true. You get Saturday Night Live here?
Yeah, on OSN.
Yeah, OSN.
On what?
OSN.
What's the OSN mean?
It's a service provider for your TV.
A service provider for your television. Okay. OSN?
Yes.
Okay. You get that in cable, like Etisalat, or?
No, Etisalat's bad. Yeah.
OSN is a different provider?
Yeah.
Yes.
So let me get this straight. Can we talk? We'll talk later. Okay? We'll talk later. Okay? We'll talk later. Okay. Now, so you have in front of you that you should have already read the test review. Much of the test review you learned in Chapter 6 on the periodic table. I'll give you for instance. Group 1, okay. Group 1 elements form +1 charges, oxidation states. Notice I say +1. Actually, if truth be told, it's 1 plus, but I say +1. Okay. And group, we're using the IUPAC periodic table instead of the American periodic table. Group 17 is -1, correct?
Yes.
Yes? Okay. So you have sodium with 1 electron, that's a Lewis dot diagram, and then you have chlorine with 1, with 7, or we'll make those look different, right? And then this goes here, and chlorine ends up with a valence shell like argon, correct?
Yeah.
And this is a 3s1 electron. Therefore, what's left is 2s2, 2p6, like neon, correct?
Right.
So this has the neon shell. So this becomes sodium +1, and this becomes chlorine -1. Because it has 1 less, the number of protons don't change because you're suggesting that sodium is still sodium and chlorine is just chlorine, and bonding has nothing to do with protons but with electrons. So the identity of the element remains the same. So it's that constant number of protons which will give rise to a charge because you're changing the number of electrons, correct? So this becomes 10 electrons like neon, and this becomes 18 electrons like argon. So this will be positive charge. This will be +1 charge, and that's -1 charge. Are we okay with that?
Yeah.
That's essentially, that's ionic bonding. Now, what would you consider to be an ionic bond? Well, an ionic bond on paper means that you have a transfer of an electron. That the difference in electronegativity is so strong that one atom literally rips an electron from the other atom, creating an ion. So I'm suggesting that this is 3.0. What's sodium? Please someone look up the electronegativity. If I ask someone to look up the electronegativity, can everybody do that? Because what happens is everybody thinks each other's doing it and nobody does it. So I know that you're really tired and you had a long vacation, but yes.
0.93.
0.9, close enough? So it's 1.1. So we're saying that any difference of 1.1, you can use that as the model example. In other words, I'm saying, well, I know that sodium chloride is ionic, right? So I'm saying that anything over 1 in terms of a difference, is that over 1? 0.9, no, over 2? Yeah, over 2. So sodium is 0.9? Is that what you said?
.93, but yeah.
So let's say 0.9 and chlorine's 3. So anything around 2, we're going to declare that ionic. Is that okay? Is that all right? Okay. So what would you say? Maybe something like aluminum chloride. Aluminum chloride. What would you say that would be? Aluminum and chlorine. Aluminum and chlorine. What would you say? What's aluminum? We know what chlorine is. Chlorine is 3. What's aluminum?
1.5.
1.5. So would you say that that's ionic?
No.
You would certainly say it's going to be polar covalent, correct? And maybe, what's hydrogen and chlorine?
Hydrogen.
0.9, right? Hydrogen is 2.1.
2.2.
Okay, 2.2, 2.1 is hydrogen. Chlorine is 3. I know that that is going to be covalent. What's my point here? My point is this. That hydrogen chloride, that's covalent. I know that that's covalent. That's called hydrogen chloride. And what I was about to say with aluminum chloride, this is what I was about to say. I was about to say, and this is going to be 0.9, the difference, yes? I was going to say this. What is this going to be? Aluminum, what's aluminum? 1.5?
1.5.
1.5. So it would be 1.5 difference. So if we're saying that that is going to be polar, very polar covalent, right? Because we know we have a shift here, right? Yes? Polar covalent. If that's polar covalent, this is very polar covalent. Right? Correct? Could be ionic. This is what I was about to say, and that's this. That under certain conditions it could be ionic. Under what conditions is this particle ionic? Hydrogen chloride. If I bubble hydrogen chloride gas into water, it becomes hydrogen and chloride ions. Okay? It becomes hydrogen and chloride ions. Right? So in aqueous solution, meaning a water solution, this is no longer covalent, but ionic. Correct? So under certain conditions, this is ionic. So I'm sure that under certain conditions, aluminum chloride is ionic. No, I have no doubt about it. But it's hard to draw straight lines when it comes to covalent versus ionic. It's hard to draw straight lines. It's hard to get a direct answer because it's really a continuum. It's based on conditions. It's based on differences in electronegativity. Yes, so it depends. Yes, as to whether or not something's going to be polar or covalent. Clear? Ionic or covalent. So let's look at the structure of aluminum chloride. We know that aluminum is in the middle. Okay, we're doing a little bit of covalent bonding now. We know that aluminum's in the middle. Chlorine is here. You know what? Let me turn this off, and we'll call this ionic bonding.
Okay.
Is that good? We'll call it ionic bonding. Okay.